So we've done all sorts of hypothesis testing. We've done testing for proportions. We've done testing for means, which is actually this section. And now we're going to talk about doing a significance test on paired data. Okay, so where do these pairs come from? Let's take a look at the first example here. It says, is the express lane faster? For their second semester project in AP Statistics, Libby and Catherine decided to investigate which line was faster in the supermarket, the express lane, as claimed, or the regular line. To collect their data, they randomly selected 15 times during a week, went to the same store, and bought the same item. However, one of them used the express lane and the other used a regular lane. To decide which lane each of them would use, they flipped a coin. That's kind of important, right? You have to have randomness. If it was heads, Libby used the express lane and Catherine used the regular lane. So the treatments were randomly assigned. If it was tails, Libby used the regular lane and Catherine used the express lane. They entered their randomly assigned lanes at the same time and each recorded the time in seconds it took them to complete the transaction. So no funny business, right? Everything was kept the exact same except they randomly chose which line they were going to go in, the express lane or the regular lane. So we've got their data here. Our job is to carry out a test to see if there's convincing evidence that the express lane is indeed faster. Okay, so then for comparison, for their 15 visits to the store, right, one of them chose the express lane, one of them chose the regular lane. So it would only be fair to compare, like during those times, right? Like this visit, this visit, this visit, if we compared those directly to each other. So the idea with pair data, it would only make sense if we compared each time they went to the store, right? We compared what was the difference in that specific time, right? Was the express lane faster that day or was the regular lane faster that day? And how much faster was it? So to say that something has paired data, we want to look at the differences in each pair. Right? And if we do that, we can see, like on average, which one was faster. So I want to find the difference between each visit to the store, right? What is the difference for each one of these? And then I want to find the mean of all of those differences. So we look at each pair, what was the difference, and then we're going to find the mean difference. And to do this, we're going to go left to right here. So we'll do express lane minus regular lane, and we'll get the difference for each one. So to start here, 337 minus 342, the difference would be -5. 226 minus 472, that's negative 246 seconds. Then we have positive 46, negative 121, negative 30, negative 55, negative 79, 94, 17, negative 95, negative 20, negative 14, negative 129, positive 39, and a negative 42. So we've got our differences for each one of the 15 store visits. So what's the mean for this data? What was the mean difference? And if you're like me, you don't feel like typing all this in and calculating it, so let's let our calculator do it. So let me get on my trusty TI-84 here. If I just tell my calculator what the data was, so I can just go to Stat and then Edit, it's going to edit a list, and I can go ahead and L1 and just enter all that data. That's a place to start. I need to tell my calculator what the data was. So I've actually already got it in here. You can go ahead and do that too, and you should know by the time you get done, you should be on entry 15. There we go. So I've got all 15 entries in my calculator here. So now that you've got the data entered, if you want to know the sample mean or the sample standard deviation, just go to Stat, Calc. The first option there is 1var stats. L1, that's the list we stored it in, so hopefully that's the list our calculator is going to use. Go to Calculate. There's our sample mean, negative 42.667, and there's our sample standard deviation, 84.0192. All right, great. And we're definitely going to need these stored in the calculator for later, so make sure you do that. The sample mean we said was about 42.7 seconds, and the sample standard deviation was right at about 84 seconds. All right, so these are going to come in handy. Let's go ahead and start with the significance test. So by now we know that starts with the whole state, plan, do, conclude, right? So for the state step, we need our hypotheses. So something to keep in mind, the null hypothesis, the one that says there's no difference between the express lane and the regular lane, that would mean the true mean difference is 0, right? So that's what we're going to use for our null hypothesis. So let's start with the state step. We want to test these two hypotheses, which for the null we know it's mu equals 0. And for the alternative, if we're suggesting that the express lane is faster, right? So that means it would take less time here. So the express lane should actually be a smaller number minus a bigger number, meaning the alternative says the true mean is negative, it's less than 0. And that's just the way we calculated it because we chose to do express lane minus regular lane. So that's why this one would be negative, less than 0. So we've got our hypotheses. Let's say what mu is, right? So mu is the true mean difference measured in seconds between the express lane and the regular lane at whatever the supermarket is that they're studying. And then one, I think, really important thing to point out to someone who doesn't know a whole lot about this problem. So are you doing express minus regular or regular minus express? So we should state that here, right? By the way, we're calculating this as express minus regular. And then don't forget the alpha level, right? We're going to use 0.05. All right, just need a little bit more room here. It's time for the plan step. So we know we need to name the test, right? And this is still going to be a one sample t-test, our one sample just being the differences, right? So we'll say if conditions are met, we'll do a one sample t-test for the true mean difference, right? So still the same test. If you use your calculator, still the same command, it's just t-test. So one sample t-test. And just to be clear, it's the true mean difference, right? These are the differences. We're looking for the true mean difference. Okay, the conditions, randomness should be good, right? They randomly selected those 15 times to go to the store. So the 15 times were randomly selected, check mark. And then as far as independence goes, I mean, one thing we could definitely say is that they randomly picked 15 times. Technically, that's way less than 10% of all the times they could have picked, right? So 15 is less than 10% of all possible shopping times. So the 10% condition would work. To be fair, they definitely did sample without replacement, I'm assuming, right? You can't sample like 2 times at the same time. So they sample without replacement, but 15 is definitely less than 10% of all the possible shopping times they could have come up with. So we're good as far as the 10% condition is concerned. Let's give that a check mark. And last but certainly not least, I need a little bit more room here. Let's talk about the normality condition. So this is still talking about means, right? So I shouldn't say anything about NPs, right? That would not make sense. You can either use the central limit theorem if you have a big enough sample size, which we don't. We only have 15. Hopefully it comes from a normal parent population, but we don't know that. So what we're going to have to do in this case is show some evidence, right? We have a small sample size. We have to give some sort of evidence and make some sort of comment about how we're going to address this normality condition. Okay, so something you could do that we've done in the past is try to make a dot plot. I really don't feel like making a huge dot plot with all these dots right now, especially considering that we've already got all these entered into L1. So let's let our calculator make a nice graph. We'll make a little sketch here and say, hey, sketch looks pretty good, right? and that'll serve as our evidence. All right, so I got my calculator out. Again, if I go to stat edit, everything's already entered into L1. Let's make a stat plot. Go to second y equals. That's the stat plot. Right? Second y equals. Plot 1, let's go ahead and turn it on. And it gives you a few choices here about which plot you should make. So my all-time favorite, my personal go-to for these questions is always bottom right here. That's a normal probability plot. Let's try one of those. So I'm going to press enter to turn this thing on, right? Turn plot 1 on. And then I'm going to go select that graph in the bottom right corner. That's a normal probability plot. That's what I want to make. Yes, L1 is the data axis, x-axis. Yes, you can use these things to mark the data points. Let's go ahead and hit graph. And if you'll notice, I can't really see. Oh, I see one dot. That's great. Otherwise, I don't see anything. Remember, there's a little bit of a trick on here. If you go to zoom, and then the 9th one down is zoom stat. Basically, it zooms in on your statistics, right? So let's use that option, zoom 9. So I press enter, zoom 9. Beautiful. There it is, my normal probability plot. Okay, and here's what this means. This line in the middle, that's like z-score equal to 0. Your calculator went through all the work to make the z-scores for each one of those data points, right? And it plotted it against its own z-score. So like this would be a -1 z-score, this would be a -2 z-score, whatever this data point was, right? One that was really negative. And then going this way, this would be +1 for a z-score, +2. So we really don't have anything beyond -2 z-scores down here or above +2 z-scores up here. And all you have to say is, look, this shows a roughly linear pattern, right? A roughly linear trend. And there's nothing that's like crazy outlier. I know this one's kind of pushing far away, but there's nothing that's like really far off as far as the pattern goes. So I really like to just make these, and then I can make a little sketch, and then I'm good as far as the evidence is concerned. Let's go back to the stat plot for a second. If I go second y equals stat plot, let's say you wanted to make a box plot, right? And let's make this one right here, the one that shows the outliers. So the plot is on. Let's go turn on this box plot. Whoops. Go up. There we go. Arrow to the right. Let's make this graph. So I hit enter. My calculator's still using L1 here. And if I go to graph, and we can hit zoom 9. It looks like it's already good on the zoom. And the box plot, it doesn't even have any outliers on it. So that's even more evidence to say, hey, look, it's not terribly skewed, right? It's definitely a little bit off, but it's not terribly skewed, right? No strong skew, and no outliers, right? So as long as we're not offended, we're going to assume this thing came from normal parents. Okay, so we got to sketch one or the other. I'm going to go ahead and sketch the normal probability plot. Right? So here's z-score equal to 0. And we can put the z-scores -1, -2, +1, +2. And I'm just going to look at my calculator and try to make that same pattern that the dots were in for my normal probability plot. So there we go. Get all 15 dots here. All right, that looks good. So there's our evidence, and then all we really have to say, we have a normal probability plot. You know, it's roughly linear. It doesn't show any strong skew or no apparent outliers. So we're going to go ahead and make the assumption that this data, right, there's only 15 data points, I know, but we're going to make the assumption that it came from a normal parent population. Cool, so now we're on to the do step. All our conditions are met. So for the do step, we need a test statistic, a p-value, and if you're using a t-score, don't forget you got to say what the degrees of freedom are, right? So let's start with the test statistic. So if we calculate this, we know it's a t-score. We take our sample mean and subtract the mean from the null hypothesis. So how far away is our sample mean from the null mean? And divide by the standard error down here. So we've already got this data. That's good. Sample mean was -42.7. The null hypothesis mean was 0. Sample standard deviation was 84. We found that. and then square root of n, so square root of 15, which should give you negative 1.97. So our t-score here, our test statistic, t equals negative 1.97. So we need to use that to get the p-value. And the p-value really answers this question. What's the probability we would get a sample mean at least this low, right? What's the probability we would get a sample mean at least this low, assuming that the true mean is 0, right? How do we answer that question? We use this t-score. What's the probability we get a t-score that low? So we can illustrate that by drawing a curve, marking off negative 1.97, and shading everything below it. So keep in mind, I'm definitely doing all this by hand, right? I didn't use the t-interval command or anything like that. I found the t-score by hand, and now for this, I'm going to use tcdf. So I'm going to find this little area, this probability, using the command tcdf. And when I do that, my calculator asks me for the lower bound, which the lower bound in this case would be negative 1e99, right? It keeps going that way forever. So negative 1e99. The upper bound, I marked it off at negative 1.97. And then the only other thing it asks for is degrees of freedom, which we know is 1 less than the sample size, so 15 minus 1 would be 14. That's really important. Make sure you know what the degrees of freedom are. And that should give you your p-value of 0.0244. So how rare is it to get a sample mean of negative 42.7, right? It's this rare, 0.0244 for the probability. All right, time to conclude. Last step for significance test, the conclude step. So we got a p-value that was really low. In fact, too low for us to believe the null hypothesis. So our p-value was low, right? So because our p-value, which was 0.0244, is less than alpha, which was 0.05, we're going to have to reject the null hypothesis. So that's great, and that's half the story. We need to conclude that in context. So can we summarize that in context? So if you're rejecting the null, if you're rejecting this claim, which claim are you supporting, right? Well, basically we have convincing evidence that it's not 0. In fact, it's less, there's less time spent in the express lane. So we have convincing evidence that the express lane is actually faster than the regular lane. And the way that's written now, that's actually not entirely true. I mean, you could point to this data right here and be like, wait, regular lane was faster on this day. So that's not true all the time, right? So it's important to note, like, all this inference that we just made was about the true mean. So we're saying that the express lane is faster than the regular lane on average. That's an important point to make. Like, yeah, obviously, sometimes the regular lane's faster. But we've found convincing evidence that on average, the express lane is going to be faster. Great, so that's your first example of doing a significance test with paired data. Really the same exact procedure. You're just you're making an inference about the mean difference, right? So there's your sample that you type into L1, just the 15 differences. All right, let's finish these notes off. The first blank here says comparative studies are more convincing than single sample investigations. For that reason, one sample inference is less common than comparative inference. In other words, one sample inference is kind of boring sometimes. So study designs that involve making 2 observations on the same individual, or 1 observation on each of 2 really similar individuals. There's a special term for that from chapter 4, by the way. Those types of studies result in paired data. When paired data result from measuring the same quantitative variable twice, we can make comparisons by analyzing the differences in each pair. So that's exactly what we just did in the first example. If the conditions for inference are indeed met, we can use one sample T procedures to perform inference about the mean difference, or, if you will, mu sub d, right? The true mean difference. And honestly, you don't have to use that notation. Some people like to because it helps them keep things straight. I'm looking for the mean difference, so they put a little d subscript on mu. Sometimes people call these paired t procedures. Paired t procedures. And as far as the inference method goes, you're really doing the same thing. You're going to do a one-sample t-test, but you're going to use the differences between each pair for your sample, like the thing that you type into L1. All right, so you got your first experience doing a test of significance about pair data and t procedures. I think that's enough for these notes, so I'll see you in class.